Pretty funny. And I'd like to thank all the organizers because I've really enjoyed this time here. So this is definitely a problem on the mathematics side of this mathematics and liquid crystals program. So it's a mathematical problem, it's a problem in bifurcation theory with symmetry that comes up in the context of liquid crystals. And I know that there was a lot of activity and discussion on this topic at the beginning of this program, and unfortunately I wasn't able to go, so I'm speaking to you. But anyway, I hope you find it interesting, and I hope also that I learn something from experts in the audience. So I'll just give some context. A number of people have studied biaxial pneumatic liquid crystals and their phases, and Valery Slastikov and I were looking at this problem. We were looking at a special case, or a two-parameter family of two-parameter specialization of the Straley potential for people who know what that means. This is the Fraser model. Anyway, so from this model you get a free energy, let's say. Depends on two order parameters, which roughly correspond to the uniaxial ordering in the phase and the biaxial ordering in the phase. And it also depends on two external parameters. And let's say one of them roughly corresponds to temperature, and the other one corresponds to the degree of asymmetry in the molecular interaction, the extent to which the molecular interaction is sensitive to the distinction between particles being rods as opposed to platelets. So you get this free energy and you expand around a point in the external parameter space, a value of the temperature and a certain type of molecular potential, where all different sorts of phases appear. And you keep some number of terms and you construct bifurcation diagrams. And then the question is, well, what about the higher order terms that you're throwing away? You don't really think that they'll change anything, but can you show it? So this is really the question that we're addressing. How do you get rid of these higher order terms? And it turns out that this normal form has some symmetry. It has D3 symmetry, the symmetry of an equilateral triangle, or really what it is in this case is it's permutation symmetry of three objects, and the three objects are the labels that you choose for the, say, principal axes of the molecular frame. So it's a problem in bifurcation theory with symmetry. And we spent some time looking at the literature, because there is a big literature on the subject, and didn't find quite what we wanted, so I thought, well, maybe I'll see if I can establish this result myself, and that's what I'll be telling you about. So I could well imagine, first of all, that the result is known, and also perhaps that this approach is known, in which case I'd be very glad to learn about it. But in any case, I hope you find it interesting. So it's a way of doing these things different from some approaches. Sometimes it's called the Moser trick. So to be a bit provocative, maybe stretching a point, you could say it's doing perturbation theory with doing non-perturbative perturbation theory. I think that's too strong a claim, but anyway, it'll become more clear what I mean. But the basic problem in normal forms, or really perturbation theory, is this. You have some problem which you know how to solve exactly, some exactly solvable problem, and then you perturb it. And you want to know, first of all, if the solutions of the perturbed problem are qualitatively the same as those of the unperturbed problem, and then if they are, to determine the quantitative differences produced by the perturbation. And a standard approach that we all use is to try to remove the perturbation in some sense order by order, sort of power series approach. This Moser trick is a bit different, and you reduce this problem of finding this transformation of coordinates, which is a nonlinear problem, to essentially a linear problem, which makes it sound simple. The nonlinear problem isn't really excised, but it reduces to sort of a standard result. It's using the existence of solutions to ordinary differential equations, but then you have to establish that these solutions really exist. All right, so what I want to do first...
You have a solution for arbitrarily strong couplings?
No. So the couplings will have, I mean, something has to be small,
right,
and things will only be local.
Then you hope as you move through the coupling constant space, you don't go to a qualitative new.
I mean, eventually you will. So, I mean, it's really not non-perturbative, and I probably shouldn't have said that. Okay. All right, so, but I want to give with sort of a simple canonical example of this approach, which is a proof of Morse's lemma. So that is, we have a function f of y, which later will be a free energy, but now it's just a function of some number of variables. And it has a critical point at 0, a non-degenerate critical point. So let's say, first of all, that it vanishes at the origin, but its gradient vanishes at the origin. And the Hessian at the origin is non-degenerate. So an example of such a function is just the quadratic form, f naught, I'll call it. That's your normal form. I mean, that's the simplest function that has these properties. And our perturbed function, you add some higher order terms to your normal form. And then the question is, can I find a change of variables? Y goes to psi of y. It should be smooth. It should be close to the identity, so points close to the origin aren't changed much. So that this change of variables brings my perturbed normal form into the original normal form, the perturbed function into the original function. So pictorially, this is what it looks like. Here are the level sets of the perturbed function. And what this map psi should do is map points on the perturbed level sets onto points of the unperturbed level sets. So here I'm taking the critical point to be a maximum or minimum, but of course it could be a saddle. So just a couple of remarks. I mean, first of all, this transformation can only be local in general, because the perturbed function might have other critical points which the normal form doesn't. So if you try to extend it, apply it to too large a neighborhood, it certainly won't work. And the other point is that this transformation isn't uniquely defined, because I can always move points around a given level set. And that non-uniqueness is a feature which will continue to appear in this discussion. All right, so a standard approach to this would be via power series. So let's say that this function f1 is analytic. So it has a power series, which I've written in this kind of condensed way using a combined index for the exponents. And then we try to express this change of variables also as a power series, which I've written here. And now we just substitute this power series in the equation and compute the coefficients order by order. And for practical calculations where you just want to compute leading order corrections, that's can be straightforward, provided you don't go too high. But if you really want to prove that this transformation exists, then you have to show that the series converges, and that can be tricky. So what is this other approach, this Moser trick? So there's the original problem. So the idea is that we introduce a parameter which interpolates between the perturbed and the unperturbed problem. We think of this parameter t as time, if you like. We switch on the perturbation between naught and t. Although this isn't a dynamical problem at all, so perhaps that description isn't so useful. So we can now, instead of a single problem, a family of problems. And we look for not a single map psi, but a family of maps, psi sub t, parameterized by t. So we can regard psi sub t as, well, we can differentiate it with respect to t. We can regard it as the solution of a system of differential equations. And the vector field which describes that system of differential equations I'll call W, but it's just obtained by differentiating psi. And then we'll impose the initial condition that when t is equal to naught, when we have the unperturbed problem, then this should just be the identity transformation. So we differentiate this nonlinear relation and compose with the inverse of psi, and we get this linear condition on this vector field W sub t. And so we can so that's what you get. All right. So
what class of functions are you taking G to be in?
Okay. So I haven't said, and it is important, but I don't want to emphasize it here. So I'll take everything to be C infinity, let's say. But many of these arguments, and I'll comment on this later, would work for less degree of regularity. And I think it's actually, potentially an interesting question with this approach, that you can actually then deal with normal forms that are less regular. Okay. All right, so there are these two conditions. That's the differential condition, which is linear in this vector field W, and then the original normal form equation. So the strategy is you try to find this vector field W sub t. It's basically a linear algebra problem. And once you find it, then you solve for this transformation psi sub t. Now, solving differential equations can't be done explicitly, but you have the standard results that tell you that solutions exist, that they're unique, that they're as regular as the vector field, provided that this vector field satisfies certain conditions. And so that's why it's not simply a problem, an algebraic problem to find this vector field W sub t. You have to make sure that it's sufficiently well behaved that then you could solve the associated system of differential equations. But that's the idea. So I'll actually go through how it works then in this example, because I'm sure many of you have seen it before, but if you haven't, it's just a nice argument. All right, but just a remark that this vector field WT is also not uniquely defined. We can add to it any component which is orthogonal to the gradient of the function. And of course, that's just the infinitesimal version of this non-uniqueness of the original map psi. All right, so this is the equation that we're trying to solve. And we note that the perturbation vanishes at the origin because, well, it's of higher order, it's of order at least cubic in y. And also, the vector field gradient of f vanishes at the origin because the origin is a critical point. So first of all, we can sort of factor out the vector y. That is, I can write the function g as a vector as y dotted into some other vector q, and I can write the gradient of f as the vector y dotted into some matrix B. So sure, you've seen this trick before, but let's see how it works for the function g. So I write g of y as the integral of its derivative, but when I evaluate the derivative, this vector y comes out, and I dot it with this quantity here, which is then my vector q sub t, and you do something similar to factor out y from the gradient of f of t near the critical point. All right, so when we substitute these two factored expressions into the condition, then we can certainly sufficient if we solve this now linear system here. So originally we had one equation, now we have n equations for y, but now that's something that we can see what the solution should be, what W should be, but the only question is this matrix B invertible? And so here's where the non-degeneracy condition comes in. So it's just a straightforward calculation. You compute what is this derivative, what is this matrix B sub t? And you can see that, well, at t equals 0, it's just the original Hessian of the normal form A 0, and then it differs from that by corrections that are proportional to t and of order y. And so for when your y is sufficiently close to the critical point, this matrix has an inverse, which is smooth in y. And therefore, we can construct the vector field W just by solving the linear system. And the vector field is well behaved near the origin. And therefore, we can solve this system of differential equations to get psi sub t at least close to the origin. So that's the idea. That's how it works. And so this idea or trick has been used in many different contexts. And so I guess Moser's original paper was on a different problem. I think in 1965, this was showing that two volume forms on a manifold can be, or isotopic, or related by a diffeomorphism if and only if they have the same volume. The integral volume form over the manifold is the same. And he used this idea to solve the problem, and it's a very simple solution once this trick is introduced, and then it's been adapted in other contexts. So there's an infinite dimensional version of Morse's lemma, which can be established then nicely using this approach. And as we mentioned already, then this doesn't require the perturbations to be analytic. So that's another difference of doing things this way. Okay, so now I'm going to start talking about the problem that we're considering, and just begin by introducing this D3 symmetry in the plane. So now there's going to be functions of two variables, x in the plane, and for what I want to say, it's sometimes convenient to think of x as being a complex number. So the action of the dihedral group in the plane is easy to describe in terms of this complex representation. So there are two generators. One is rotation by 120 degrees. The other is reflection about the horizontal axis, or complex conjugation. And then it's easy to see that there are two invariants. First of all, the modulus of z, or modulus of z squared, is obviously invariant under these operations. Z cubed is invariant under rotations by 120 degrees, and the real part of z cubed is then invariant under complex conjugation. So Those are two invariants of this action. And if you have a function which is invariant, it just means that its value isn't changed. And such a function then can be expressed as a function of invariance. So I'll use the convention big F for functions of the original variables, or big letter for the function of original variables, and small letter for the corresponding function of the invariance. Okay, so now I'll introduce this normal form problem. So we've got some function, call it f naught, which is depending on variables x, but also on some external or additional variables, which I'll call a, also living in R2, and they'll be regarded as small as well. And I'll take f naught to be of this form, expressed in terms of the invariance. It's written like this, linear plus quadratic term, and the linear term is small in these parameters a. So that's the normal form. And then we'll consider a perturbation of this normal form. So we'll add to it some function g, which is of higher order, so either of order y cubed and higher, or of order ay squared and higher. And we ask the same question that we had before. Can this perturbed function be brought to normal form by a change of variables? And the answer is yes, but you have to do more than change the variables. So this is what you have to do. First of all, the change of variables, the change of these x's, is going to depend on parameters as well. So for different values of parameters, the transformation looks a little bit different. You also have to rescale the energy. So that is, you multiply the energy by a constant, which depends on parameters a. And of course, rescaling the energy doesn't change the critical points. And this scale factor is going to be close to 1. And finally, the parameters themselves have to be transformed. Again, this is a near identity change of variables. So that's what I'll be going through later. But first, I'll just give some motivation for where this normal form comes from biaxial pneumatics, and then run through the bifurcation sequence of this unperturbed normal form. And this will be familiar to many of you, and I think you've all, in the course of this program, been on this journey a number of times, so I'll take you through it again, maybe a little bit quickly. Anyway, so this is one approach to getting a free energy for, in this case, biaxial pneumatics. So I'll take a molecular point of view, although in the end you could just say, well, there's no particular advantage to thinking it through this way as opposed to using a Landau theory argument, because the connection with the molecular theory is perhaps rather tenuous, or not expected in practice to tell you anything more than a phenomenological theory. But anyway, I'll proceed. So we have a gas of particles characterized by their position little r, but also their extended objects, and we'll characterize their extent by their orientation, which is a rotation matrix. And so we have an n-particle density for these particles, and free energy associated with densities, which is just the usual one. And the minimizer is, of course, just the Boltzmann distribution. But we can't compute the Boltzmann distribution, so we vastly simplify the problem in an uncontrolled way. We won't consider all possible distributions, but distributions which are, first of all, spatially inhomogeneous and also uncorrelated. So really just determined by a single distribution function for the orientation r. So that's what I'm calling rho 1. And when you substitute the densities of this form into the original free energy, then you get a one-particle free energy, which looks like this. And there appears here an effective orientational interaction, which depends on the orientations of the two interacting particles. I should have said that we're just assuming they're two-body interactions. But really what it depends on is sort of the effective or frame-independent relative orientation of these two objects. So what do we take for the potential? Well, sort of the lowest order non-trivial potential is quadratic in the components of R. And there's a general form which is consistent with all the symmetries that was determined by Straley, and it has 3 parameters. And I'm going to talk about a restriction that's been considered by many people where we limit it to 2 parameters, and Epifanio has studied other restrictions, and Tim Slukin and David Chillingworth have studied this problem extensively. So everything I'm saying here, I think, is well known. Anyway, so we study this particular form of this two-particle potential, and then you can show, and in some cases it's not easy to determine what the critical points look like, but for this particular problem it is. You can show that the critical points of this one-particle densities are densities of this form. So it depends on two order parameters, which I'll call little x1 and little x2, which appear as in this expression in the form of a matrix, and I should have introduced these this basis for traceless diagonal matrices, which appear in these problems. But I don't need to go through so many details anyway. And then how are these order parameters determined? Well, they're critical points, or they're determined by requiring that this one particle density be a critical point of this one particle energy functional. And then you see that this has some symmetry. It's symmetric under relabeling the principal axes of the molecular frame, which in terms of these order parameters just translates into this D3 symmetry in the plane of these parameters. And so then you can't, and from this, at least from this molecular derivation, you can't evaluate this free energy explicitly, but you can expand it near certain points, and in particular, first of all, near the isotropic point, but also near values of the parameters which appear in the potential, which correspond in some sense to a weak interaction, but one which is also maximally asymmetric because it's in the neighborhood of such a point that all phases appear. And you get a free energy which, when you expand it in terms of the invariants, remember these big Y's are the invariants under D3 symmetry, and the A's are the parameters which are related to these sigmas, but I'm leaving out details. And then you have to do some rescaling. But anyway, you get the normal form that I wrote down previously. So the critical points are not given by critical points of this function little f1, but of the proper free energy big F1. And you can identify the different possibilities. Of course, from the point of view of physics, you're really not interested in all critical points, but just minimizers, really. But you can ask about all critical points, too, because, well, to change parameters, stability can change. Okay, so first of all, there's, of course, the isotropic phase that corresponds to the invariance being 0 as well as x being 0. And in this phase, the corresponding one particle density is uniform. There's no preferred orientation or no preferred relative orientation for the molecules. The next type of critical point are critical points of this type where the values of the invariants are parameterized by a single variable s, and these, when they're related in the way indicated, this corresponds to a uniaxial phase, which means that the corresponding one particle density has an axis of symmetry. Somehow the relative molecular frame doesn't care about relative orientation with respect to a preferred long axis. And when S star is less than 0, corresponds to a prolate distribution where this preferred axis tends to point in a particular direction, and S star greater than 0, and it just corresponds to the case where this preferred axis wants to lie in a plane. And finally, when the values of the invariants aren't so related, then you have a genuine biaxial state, which corresponds to a distribution, probability distribution for relative orientations, where there really is one preferred orientation. Okay, so now I'll just take you through the bifurcation sequence, and maybe I'll just flash through these so just so you can see what's moving, and then I'll go back.
Sorry, can I ask one thing?
Sure.
So how is this rescaling of the energy
So it's two things. It's rescaling the magnitude of these order parameters, and also rescaling energy, so choosing appropriate units for the energies, and then you can express it in this form. But if you use the original parameters, you actually get explicit coefficients for the quadratic term, which are not the same, but they have definite values. And you can compute what they are. But it's just there. Okay. So here are the external parameters, the A's, and here are the Y's. These are the values of the invariants. So these are really labeling the order parameters, but they're these invariant combinations of the order parameters. And this area between these two curves is sort of the corresponding to values of the invariance that are realizable, let's say. This is the image under the, this is the set of, inside here is the set of values of the invariance taken by points x in the original parameter plane. So I'm going to be moving across a line in parameter space, and roughly speaking, the horizontal axis corresponds to temperature, so we'll be cooling things down. And the vertical axis will be, the vertical coordinate is 0. This corresponds to a maximally asymmetric interaction. We'll offset that, which gives sort of one preferred direction. And then we'll see pneumatic states appearing. So as we move across, when we start here, there's only one critical point corresponding to y equals 0. That corresponds to the isotropic state. And at this point in parameter space, then there appears a degenerate uniaxial critical point. And uniaxial critical points are going to lie in these boundary lines here. And as we increase the parameter further, then these split, and you have two prolate states, one of which is metastable, or at some point it becomes the global minimizer, and the other is the saddle point. And then when we get to the vertical axis, there's a bifurcation between one of these prolate states and the isotropic state. And then as we proceed to still further, now the isotropic state now has become unstable. This uniaxial state has become prolate, it's a saddle point, and the oblate pneumatic state is now the preferred state. And then when we increase the, or decrease the temperature further, now the oblate state undergoes a bifurcation, and when we decrease the temperature further, there appears now a biaxial critical point, which is the minimizer, and the uniaxial critical point has become unstable. So that's the bifurcation sequence that you see in the vicinity of the origin of this parameter space. And so now come back to the normal form problem. So the question is, you compute the lowest order terms, you throw away the rest, and is this bifurcation sequence preserved? I mean, could anything change by higher order terms? And you don't expect it, but the question is, can you establish that that's the case? So here I've just reiterated this normal form problem. So here are the invariants. I've written them now in terms of x's rather than z's. Normal form is this function f naught of the invariance, which is a linear and quadratic term. Here's the perturbed normal form, which has this additional term, which is of higher order in the a's and the y's. So again, the question, can it be brought by normal form? Can it be brought into a normal form? And I'll repeat the answer, but give a few more details this time. So first of all, the change of variables now is going to be parameter independent. So x, the map psi is going to depend on the parameters a. It's going to be near identity. It should also respect the symmetry. The energy should undergo a near unity rescaling. And I've written the rescaling factor as an exponential just because it's convenient to do it, but the idea is that this factor is something that's close to 1. It's 1 plus corrections of order a. And finally, the parameters themselves have to be transformed. Again, it's a near identity transformation. And so how to find these? So again, we'll use this idea of making, well first, just to make the writing a little more condensed, let me leave off arguments and just write it in this more condensed way. So that we're trying to find scaling factor A, coordinate transformation psi, and parameter transformation chi into normal form. So we'll again use this Moser trick. We'll make these transformations dependent on a variable t by making the perturbation proportional to t, and try to find now a solution for all t. And we'll think of these transformations chi, psi, and a as being flows of associated vector fields, which we compute what they are. So I'll be referring to these things later on. So the flow of the chi, this is parameter dependent change of variables, I'll call associated vector field z. The flow of the coordinate transformation psi, I'll call w. And this is actually a coupled system of ODEs now because psi is depending on both the x's and the a's. And then finally, the scaling factor satisfies this equation here, which can be reduced to ODEs. So as we did before, we differentiate this with respect to time and compose with the inverse of these maps. And now we just get a linear condition on these vector fields z, w, and lambda, and here it is. And provided you can find them so that this linear condition is satisfied and they're sufficiently regular, then you have the solution. So it's the same strategy as before, but we face the same issues as before, namely that these vector fields aren't uniquely determined, that this linear conditions, it's not necessarily obvious that they can all be satisfied, and we have to show that these things are sufficiently well behaved that everything will work. Okay, so that's the setup of the problem. And well, I've gone too quickly, I guess. Well, so this will finish kind of early. So what follows, and you can see I'm on 17 to 22. So what follows is some information about the solution. And I guess first I thank you for paying attention up to this point. But what follows is, so there is a solution, and it takes some work, and I wasn't planning to go through it in any sort of detail here. To me, it's interesting that the problem can be solved, because it doesn't seem, at least it didn't to me, that it was necessarily the case. So there's some interesting features which maybe can be understood from a better perspective or can be generalized, which aren't clear to me. And I just wanted to try to convey these features, but in probably a clumsy way, because there'll be equations which I won't explain what everything means, but the main point is just to sort of convey what the issues are, what arises, and maybe also there'll be something that people will recognize and be able to tell me more about it. Okay, so that's my pause, and now I'll continue. So here's this linear condition, this linear constraint that has to be satisfied, and we just have to find fields that satisfy them. So this is depending on both the x's and the a's, but the first observation is that if we evaluate this system at one of the critical points of the perturbed normal form, then this term involving the vector field W goes away, and we're left with a system that just involves lambda and z, which depend only on A. And basically the idea is that, well, we don't know what this transformation psi is. Well, you don't see psi anymore, but you don't know what it is, but you know what it does at certain points. It has to map the critical points of the perturbed normal form into the critical points of the original normal form. And the critical points of the perturbed normal form you can determine without knowing anything else. So these are constraints which must be satisfied, and these will enable us to determine, first of all, lambda and z, and then we'll go back and determine w. So reminder, z is describing how the parameters change with the perturbation, lambda is describing how the energy is rescaled, and g, little g, is the perturbation. All right, so first of all, so let me go through the critical points of the perturbed normal form, and one of them is, of course, the isotropic critical point, but this condition is automatically satisfied there. So we have other critical points to determine, or other critical points at which to evaluate this condition, and there are in general, or at most, 2 uniaxial critical points and 1 biaxial. And so we get 3 conditions from this equation, which looks appropriate because we actually have 3 unknowns. Lambda is a scalar and z is a vector with 2 components. So we're getting 3 equations or 3 conditions and 3 unknowns, 3 linear conditions. So there's a prospect of solving it, but it's not immediate because, first of all, these biaxial critical points, the uniaxial critical points aren't defined for all values of A, or if you like, outside of a certain region where they appear, they become complex. And they're also not differentiable functions of these parameters. So solving in terms of them won't necessarily give you nicely behaved vector fields. So again, this issue of whether you can solve these equations and whether the solutions are sufficiently regular comes up. So first of all, that problem can be resolved as follows, that while the s plus and minus are roots of some, well, for polynomial perturbations, it's roots of some polynomial, and they determine the values of the corresponding invariants of the critical points. Anyway, you can show that symmetric combinations of these 2 roots are actually smooth functions of the parameters, at least near the origin. And if you're given any function h, and h is standing for any one of the coefficients in these linear systems, and these coefficients are being evaluated at these different uniaxial points, the sum of these two, the sum of the values of the functions at these 2 points, and that should be a minus sign there, the difference divided by the difference of these two roots, will also be a symmetric function in S plus and S minus, and therefore can be expressed in terms of these smooth things. And so now you get an explicit solution for this linear system, which I've written in this symbolic way. Now, the denominator, this determinant of this matrix M, I'm not saying what it is, it can vanish. But it turns out that both the denominator and the numerators vanish on the discriminant of this perturbed normal form. Well, it should really be a big F of t. That is, the discriminant is the function of parameters A, whose 0 set gives you the locus of bifurcations. It's a function which vanishes when critical points coalesce. And if you compute, so I'll call the discriminant P, if you compute the order of these determinants, determinant of M is, well, to leading order just P, whereas the numerators are to leading order P plus times some higher order term. So the solutions are, in fact, regular near parameters A equals 0, and you can determine their order, which you'll want to do. All right, so now we know what the two of these generators are, the simpler ones, because these are the things that only depend on parameters. Now we want to know how the coordinates change. That's described by this vector field W. So first of all, let's go back to the fact that we want this coordinate transformation to respect this D3 symmetry. It should be equivariant with respect to D3 symmetry. And at the level of the vector field, that means that the vector field should be a combination of gradients of these invariants big Y1 and big Y2 with coefficients C, C1 and C2, which are depending only on the values of the invariants. So when we substitute that in to the original linear condition and now take account of what we've learned by evaluating that condition at the fixed points, we get the following single condition, which involves only these, what remains to be determined, these C's. And there appears this 2x2 matrix K, a quadratic form, which is the dot product of the gradients of these invariants, written here. And the right-hand side is depending on the perturbation, but also on the vector fields lambda and z that we've previously determined. So we just have to solve that, find its C which satisfies that condition, and then we're done. So first of all, we can argue, as we did at the beginning in this case of Morse's lemma, that both sides, these are both functions, they both vanish at the biaxial critical point. So we can factor that out. We can actually factor out the gradient of this perturbed normal form here. And when we do, then we go from one condition to this linear system, as we did before. K times C is equal to some right-hand side, where on the right-hand side there's this indeterminacy because I can always add, effectively, it's like what we had before, I can always add something that's orthogonal to what I was originally taking the inner product with. That's this term here, so this coefficient alpha t can be anything. But is the solution side of this linear system going to be well behaved? And that's going to depend on alpha of t, and it's not clear that it will be because K is, first of all, small when the invariants are small, so the inverse will be large, and its determinant vanishes not just at the origin, but on the set of, let's say, uniaxial points. It was the red curve in the original, in the bifurcation diagrams that I showed. So there are issues about, first of all, whether the system can be solved everywhere, and if it can be solved, whether things are regular. And it turns out there is a solution, and I'm just putting up the formulas, but it was really by trial and error. So I think I would guess that there's probably some maybe systematic way of seeing this, and maybe generalization. And again, I would not be surprised if somehow this is yeah, I'll find this written down somewhere. But anyway, right now I'm got to the end of this story. So the point, yeah, so if you find this undetermined coefficient alpha, which then makes this vector field W well behaved as it should be, and then you don't find this coordinate transformations explicitly. You have to solve some differential equations, but you know that those solutions exist, and if you wanted to find them, you could. So that's really brings me to the end. So now just go through some questions. I mean, it would be interesting for us to see, or I should want to know how this is related to other approaches, one of which is based on sort of systematic elimination of terms in power series. But as I said earlier, I mean, one advantage of this Moser trick is that it allows you to deal with perturbations which are not analytic or have some finite amount of smoothness, and it's maybe interesting to push that, because you can imagine situations where these vector fields are sufficiently irregular that, let's say they don't satisfy, I mean, this is kind of speculating, they don't satisfy Lipschitz condition, but they might be continuous, so you know that solutions to these ODEs exist, they're just not unique. And what sort of perturbations would produce that situation, and what sort of normal forms, what does it tell you about those sorts of perturbations? And then also, so I just described this for a particular symmetry, D3, and it involved some work in order to make everything fit. And it would be interesting to see whether there's some general approach for symmetries, and then I think some more general ideas would be needed in order to do that, and also to make this sort of seem more make it easier to make sense of it. Okay, so that's what I wanted to tell you. Thanks.
Thank you, Jonathan, for your talk. Is there any question, comment?
We've had a few conversations about this, but yeah, if you insist on smooth, everything is smooth, and as you said, it does indeed fit into the general framework of
Right.
G equivariant unfoldings and determinacy. So there's a machinery out there, but it'd be interesting to find exactly how your hands-on calculation kind of relates to this general story. Sometimes the general story can be powerful, but it can kind of obscure, what's actually happening in any given case. You could think of that a bit more closely.
There isn't anything crucial about the discreteness, is there, in your method?
I just haven't really thought about it. So.
I think the answer is no. I think any compact Lie group.
Okay.
I think we have a question here.
I have one question, on comments. The question is, how is your approach embedded in general scheme of general theory of classification of regular mapping from two-dimensional? So it's Whitney theory, and so it's great theory. Is it possible to imagine use a more detailed study of some classes of embeddings? So you determine this more.
First question.
What?
That's his first question.
It's first. So this is first question, but maybe more detailed. And the second about third, because what I studied several years ago, the following problem. It's in concrete case of caustics, but it's more general. So if you have, for example, caustic which is invariant under some group, but you consider for the group SO3 and subgroups which conform. And what was interesting, what we mentioned, that there are some duality between, if you have symmetry between groups, so like Platonic solids, octahedron and cube and so, there is reflexing symmetry of caustics. And so what your approach is very useful if you consider different normal forms, so it's possible maybe to do it and consider what is breaking symmetry, for example, in biaxial pneumatics and pneumatics, so you consider breaking from Z2 cross Z2 to SO2 to Z2. So maybe it's interesting to compare with your.
Okay. I'll be happy to talk about that.
I have a quick question. I mean, I know it could be maybe considered an unfair question, but let me ask it anyhow. What is the prospect, seen from your perspective, that this kind of machinery can also be applied to the complete straight A model?
Okay, so what I would say is that the first thing with a complete Straley model that you would want to do is to study the normal form itself, which is already a big problem because it has three external parameters and 7 order parameters. I think if you consider the full problem and remove all the symmetries, that's what's left. So even analyzing the normal form is already, anyway, I don't know how to do it. I don't know if anybody has done it. So
Assuming, for example, that the 2 frames coincide and you go back to 4 scalar order parameters, is that case is clearly easier because instead of 7 you have 4. But is there any chance that this kind of approach can be used there?
What this approach tells you is once you've found the right normal form, it tells you that, then it allows you to establish that, in a sense, it is the right normal form, that nothing changes when you add higher order terms. But finding the right normal form is, of course, a separate problem.
And have you attempted this, or
No.
anyone has?
Not that I know.
So let us thank again Jonathan for